Welcome to Lecture Online, and today we're going to be delving into a new era of physics, or new area of physics, you should say. Also era, because this is something that's more recent in history, called modern physics. And so the first topic we're going to cover is the photoelectric effect. Matter of fact, the discovery of the photoelectric effect is what got Einstein his first Nobel Prize in 1905. So this is actually fairly recent, only 100 years old. So what this is all about is when you have a metal, in this case we're going to assume the metal is sodium, and sodium of course will have free electrons. Electrons are easily removed, they easily go from one atom to the next. When we have these electrons near the surface, if a photon comes down and hits the electron, it could impart enough energy on the electron for the electron to jump free from the metal. But in order to do that, you have to overcome what we call the work function. So I use the letter W to indicate the work function. And to overcome the work function, you have to impart enough energy, in this case for sodium, 2.7 electron volts, for the electron to jump free. If the incoming photon has enough energy to make the electron jump free, it can then have whatever leftover, the electron will use whatever leftover it has to then gain kinetic energy. So the question then is, how much kinetic energy will the electron have when a photon comes in? Now let's say we have a photon coming in with a wavelength lambda equal to 500 nanometers. Okay, so will the electron, first of all, will that have enough energy to make the electron escape the sodium metal? And is there any left over for the electron to have some kinetic energy? All right, so the equation then goes, any kinetic energy that the electron may have is equal to the energy that comes in from the photon minus the work function, energy required to overcome the work function. So if the energy of the photon is large enough, greater than the work function, the leftover will then become kinetic energy for the electron. All right, so we need to figure out what the energy is of a photon that has a wavelength of 500 nanometers. And we can say that the energy of the photon is equal to the Planck's constant h times the frequency of the oscillation. And since we know that the speed of light is equal to the frequency times the wavelength, we can then say that f can be written as c over lambda. So from here we can say that f, the frequency of the photon, is equal to the speed of light divided by the wavelength, and we can then substitute that back in over here. So we can say that the energy of a photon is equal to h c over lambda. So we now relate the energy to the wavelength. So we can plug that in here. So the kinetic energy is equal to hc over lambda minus the work function. Of course, the work function does depend upon what metal we're dealing with. All right, plugging in the numbers, this is equal to 6.626 times 10 to the minus 34. That would be joules times seconds, if you want to know the units of Planck's constant, times the speed of light, 3 times 10 to the 8 meters per second. And divide the whole thing by the wavelength, which was given to be 500 nanometers, so 500 times 10 to the minus 9 meters. Okay, we subtract from that the energy of the work function. Now the work function is given to us in electron volts, so that's 2.7 electron volts. And since this is going to be expressed in terms of joules, we probably want to express that term in joules as well. Or we can convert this to electron volts, and then we have kind of a way to look at it. So let's do that. Let's go ahead and convert this to electron volts. So we're going to multiply this times, or divide this by 1.6 times 10 to the minus 19 joules per electron volt, and this will then convert the units of joules into units of electron volts. All right, now I'm going ahead and calculate that. Of course, I forgot my calculator again, so let me run down real quick and get my calculator. Be right back. Now that I have my calculator, let's plug in these numbers, see what they end up to be. 6.626 E34 minus times 3 e to the 8 divided by 500 e to the 9 minus, and divided by 1.6 e19 minus equals, and this is equal to 2.48 electron volts minus, of course, the work function of 2.7 electron volts. And notice here that there's not enough energy in a photon with a wavelength of 500 nanometers to set this electron free. So the answer is, there is no answer. There's no kinetic energy that the electron will have because there was not enough energy to set the electron free. However, let's change the problem just a little bit. let's say that instead of 500 nanometers, we now have a wavelength, a photon with a wavelength of 400 nanometers, so that would be purple light. In that case, let's see, the only thing I would change is let me use a red color so you can see the difference. So now let's say that instead we use a photon that has a wavelength of 400 nanometers. Does that have enough energy to set this electron free? Well, let's find out. So that would be divided by 4 times 5 equals, and sure enough, if we do that, and we go through the whole calculation again, and let me use red again, so this would be equal to 3.11 electron volts minus, and of course we still have the 2.7 electron volts for the work function. And now you see, yes, there would be sufficient energy within the photon to set the electron free. And not only that, the remainder would then be put into the electron to give it kinetic energy. So the difference, so that would be 3.11 minus 2.7. And so we have 0.41 electron volts, and that would then be the kinetic energy of the electron that was set free. Now, of course, let's convert that back to joules. And again, the conversion to joules would be, we have joules, we have electron volts, 1 electron volt, that has to be a little bit bigger. 1 electron volt is 1.6 times 10 to the minus 19 joules. There we go. And so times 1.6 E19 minus equals, and that would give us 6.56 times 10 to the minus 20 joules. So we can either express in terms of electron volts or express in terms of joules. So again, to review what we just did, the photoelectric effect is an interesting phenomenon where we have electrons embedded within the surface layer of a metal such as sodium. Every metal has what we call a work function, the energy required to set an electron free from the metal. That work function is usually expressed in terms of electron volts. If you want to convert electron volts to joules, you can do it like this. And then we know that if the energy contained within the photon has sufficient energy to overcome the work function, in a way to say that, and then of course the energy of a photon can be calculated as a Planck's constant times the frequency, which can also be expressed as hc over lambda. And then, so this is the energy within the photon. We subtract from that the energy required to set the electron free, the work function. The remainder is the kinetic energy. In some cases, the photon does not have enough energy, so no electrons jump free. In some cases, it is enough. Electron jumps free. The remainder, the difference, will then be the kinetic energy of the electron. And that's how you do that.